Noise in measurement systems, film number 4, is about how to reduce noise. And we will go through several different techniques. It's of course not the full set of techniques, and they are also presented quite briefly here in this film. Anyways, technique number 1 is about how that we can use separation. We can separate cables from each other, or separate the signal cable from the problem area. That would influence both the capacitive coupling and the inductive coupling, because here you see the distance here is in the denominator, and also here the distance is in the denominator. So if the distance becomes larger, well, then both the capacitance and the inductance becomes smaller, and thus the inductive coupling or capacitive coupling becomes smaller as well. Also for radio frequencies coupling, you can use this technique. We all know that the further you get away from the radio source, the weaker the signal. So it would help here as well. Number 2 is twisting, and we looked at it already. This drawing was of course much better than the one that I drew in film number 3. But you see here how the magnetic field is, if you have two parallel conductors, the magnetic fields work together to form a magnetic field that go through into the center of the two cables like that. But if you twist it, the effect from the magnetic field will zero out over a distance. So the neighboring cable running close to it will not be infected overall by the magnetic field, even though it's affected by it, but it will zero out over a given distance. You can use shielding, and you have something called an overall shielding, or you have shielding of the individual pairs in a cable like that. And this one is commonly used to avoid radio frequency coupling, and this one reduces the capacitive coupling, because what happens in this conductor doesn't determine what happens in the other conductive pair. Here you avoid having signals from neighboring sources of noise going into the conductor like that. And of course, in many cables you have both elements. You have both the individual pair shielding, and you have the overall shielding like that. You can use something called differential amplifiers, which is basically just that you take one signal that is here, and you do plus minus, and then you send it over to the next step. So if you have your signal here plus your noise here, and this you are able to conduct the noise only here, well, then you will have here signal plus noise minus noise makes signal only. But that, again, that depends that you are able to isolate the noise and send that into the system alone, like that. That is actually what we talked about earlier. What happens when you have this noise cancelling headset, for example, then you're able to do things like that, if you're able to isolate the noise itself. Filtering. If you know the nature of your noise, and for example if your noise is a high frequency noise, you can use something called a low pass filter. A low pass filter will let through low frequency components and filter out high frequency components. So in this example here, I have a signal and there is high frequency noise on top of that signal, when I use a low pass filter, I remove the high frequency component, so it becomes like that. Even though I hate PowerPoint animations, in some cases they are actually quite useful. High pass filters will remove the low frequency components and keep the high frequency components. So here we have a mix of high frequencies and low frequencies. The low frequency is represented by a bit more than 2 complete waves, while the high frequency is represented by like some 50 waves or something. Let's see what happens when I remove the low frequency part and let the high frequency pass through. Well, that's how it looks, just keeping the high frequency component. A band pass will actually remove high frequency and low frequency and keep the frequency in the middle. If you see here, we have a very high frequency that makes more or less a gray band on top of the wave. I have a very low frequency with one wave only, more or less. But then I have something in the middle with 1 peak, 2 peaks, 3, 4, 5, like 10 peaks or something throughout the signal there. Let's see what happens when we remove the really low and really high frequencies and just keeping the one in the middle. And finally, band stop, which is quite useful for noise reduction. If we have, for example, a specific noise at one specific frequency, we can remove that specific frequency. And here it's we remove the mid frequency, which is the one that is represented by about 20 tops in this signal. And we keep the low frequency, which is represented by a bit more than 1 wave, and a very high frequency, which is represented by, I guess, 100 waves or something, and then 100 full waves, and then remove the one that is in the middle, which is represented by something like 10 waves, so 10 complete waveforms. 3 other techniques just mentioned briefly. Modulation is that if you have your signal here, and this is also where you have your noise, for example, represented by that peak there. And this is, of course, in the frequency plane. So you want to shift your signal to a higher frequency up here for a short time, and then shift it back. So this is actually what happens in radio signals, where in the studio we have treble, bass and mid frequencies from about 20 to 20 kilohertz, and on the radio waves it's sent by a given amount of kilohertz or megahertz. So it's shifted upwards to a new frequency and then shifted back again to the low frequencies in our receiving radio. And you can also use this technique if you have a problem along the line at a given frequency. Remove your signal outside that frequency and shift it back when you come to the receiving end of the signal. Averaging, quite common and quite easy to use actually. This is where you, if you have a bit of noise here, a noisy signal, and then you just do the average. So you actually, if you have a noisy signal like this, for example, time and voltage, for example, you know that the average is here. So you do the average over a given time interval in order to remove the noise, and that would actually be to remove high frequencies. So it's a form of a low pass frequency, low pass filter, sorry. Because if you take the average, you remove the fast shifting components of this noisy signal. Then you have something called autocorrelation, which we will not talk too much about today, because we will come back to it when we look at flow measurements actually. But it is that you try to recognize your signal by comparing it to itself at a later moment. So it's a bit advanced, but it's a technique to detect repeating signals that repeat themselves. You can find them if they are buried in noise. Bit advanced, but we will come back to it as I mentioned earlier.